Electric trains are a marvel of modern engineering, seamlessly blending power, efficiency, and precision to transport millions of people and goods across vast distances. But how exactly do they work? From the collection of electricity through overhead lines to the intricate systems that power the motors, electric trains represent a fascinating interplay of technology and physics. Let's dive deeper into the mechanics of electric trains, unraveling the complexities behind their operation. The basics of electric train operation. At its core, an electric train operates by drawing electrical power from overhead lines and converting it into mechanical energy to drive the train's wheels. This process begins with the collection of electricity and ends with the grounding of that power through the tracks. The simplest version of an electric train consists of a sliding wire that collects power from the overhead lines. This power is then fed into a single-phase induction motor, which is directly connected to the train's wheels. To complete the circuit, one terminal of the induction motor is grounded. This grounding is achieved through a connection to the wheels via axle brushes, which are in constant contact with the tracks. Since the tracks are grounded, the current flows from the overhead line, through the induction motor, and finally into the ground via the wheels and tracks. As the current flows through the motor, it causes the rotor to spin, turning the wheels and propelling the train forward. However, as the train moves, the grounding circuit needs to be continually re-established, making it essential that the track remains grounded at short intervals. Axle brushes play a critical role in the basic design of an electric train. These brushes are typically made of carbon and are attached to the rotating wheel. As the wheel turns, the brushes maintain contact with a disc attached to the wheel axle, allowing the current to transfer to the wheels. This seemingly simple component is vital for ensuring that the electrical circuit remains intact as the train moves along the track. Without these brushes, the train's wheels would not be able to complete the circuit, preventing the motor from receiving power and causing the train to stop. While the basic design of an electric train is functional, it requires further refinement to handle the high voltages used in modern rail systems. The electricity supplied through the overhead lines is typically at a very high voltage, around 25 kilovolts kV. However, the motors that drive the train's wheels require much lower voltages to operate efficiently and safely. This discrepancy necessitates the use of a transformer. A transformer is a device that steps down the high voltage from the overhead lines. The electrical supply first passes through the primary winding of the transformer. The transformer then induces a current in the secondary winding, producing a lower voltage that is fed to the motor. This step-down process is essential for ensuring that the motor receives the correct voltage, preventing damage and ensuring efficient operation.
To achieve the high torque required to move a heavy train, a three-phase induction motor is the ideal choice. Unlike single-phase motors, three-phase motors can deliver a more consistent torque output, even when the motor's speed varies. This uniform torque is crucial for maintaining smooth acceleration and deceleration, which is essential for both passenger comfort and the safety of the train. Electric trains use a combination of rectifiers and inverters to convert the single-phase AC power collected from the overhead lines into three-phase AC power. The process of converting single-phase power to three-phase power begins with a rectifier, which converts the AC power into DC power. This DC power is then fed into an inverter, which converts it back into AC power, but this time as three-phase power. This three-phase AC power is then used to drive the induction motors that turn the train's wheels. To further increase the torque output, a transmission system with a specific gear ratio is often added between the motor shaft and the wheel axle. This allows the motor to operate at an optimal speed while providing the necessary torque to move the train. With this setup, the electric locomotive is ready to pull a train along the tracks. While a single motor may be sufficient to power a basic electric train, a full-sized locomotive requires more power to pull multiple coaches. To achieve this, electric locomotives are equipped with multiple motor wheel pairs. An engine bogie, which is a framework that holds the wheels and axles, is typically fitted with three-phase induction motors. This setup allows the locomotive to drive 3 pairs of wheels, providing the necessary power and traction to pull a heavy train. In most locomotives, 2 such engine bogies are used, providing a total of 6 motor-driven wheels. The additional motors ensure that the locomotive has enough power to accelerate quickly, maintain high speeds, and climb steep gradients, even when pulling a full load of passengers or cargo. The transformer, rectifiers, and other electrical components are carefully positioned within the locomotive to ensure optimal performance and reliability. A pantograph is a device mounted on top of the train that maintains contact with the overhead wire, even as the train moves along the track. Modern pantographs use a pneumatic mechanism to adjust their height automatically, ensuring that the current collector, the part of the pantograph that touches the overhead wire, remains in contact with the wire at all times. This height adjustment is crucial for maintaining a steady flow of electricity to the train. The pantograph is designed with a 4-bar linkage mechanism that keeps the current collector perfectly horizontal, regardless of the height adjustment. This ensures consistent power transmission and minimizes the risk of power loss. If you've ever looked closely at the overhead lines above an electric train, you might have noticed that they don't run in a straight line. Instead, they are arranged in a zigzag pattern. This design is intentional and serves an important purpose: to minimize wear and tear on the pantograph's collector head. By arranging the line in a zigzag pattern, the point of contact between the collector head and the wire changes continuously, distributing wear evenly and extending the lifespan of both the pantograph and the overhead wire. Acceleration is important for trains, but equally crucial is the ability to control speed and stop the train safely. The operation of an electric train involves a complex interplay of electrical and mechanical systems, each working in harmony to provide efficient, reliable, and safe transportation. From the collection of high-voltage power through overhead lines to the use of transformers, induction motors, pantographs, and advanced braking systems, every aspect of an electric train is designed with precision and purpose. Understanding the engineering behind these systems not only deepens our appreciation for this mode of transportation, but also highlights the incredible ingenuity that goes into making electric trains a cornerstone of modern rail travel.